Charge is a slightly mysterious entity. If somebody asks you to define charge, it's hard. It's one of those fundamental concepts that is hard to grasp at. It's essentially a property of certain particles that determines how they interact with other charged particles. If they both have the positive flavor, then they repel. If they have opposite flavors, positive and negative, then they attract. And so begins story. And then if you have a charge that's moving, it generates a magnetic field as well as an electric field, and all hell breaks loose. So charge carriers are particles which possess a positive or negative electric charge. Not all particles are charged, of course. You can have plenty which are neutral, and they don't have electric fields and they don't generate magnetic fields. The SI unit of charge is the coulomb. So it is in fact an SI unit, along with kilograms and meters and seconds. So there must be something pretty important about charge if it's earned its space among one of the 7 SI units. The electrical fields around charges cause attraction or repulsion. So if you have a negative charge on its own, it'll form a radial field pattern. Same with a positive one. For the convention when we draw fields is that the arrows flow in the direction that a small test positive charge would go. So for that reason, if I did put a tiny little positive charge here, tiny enough that it doesn't generate its own field is the thinking, it would be repelled by the positive charge. Therefore, the arrows go outwards. And for similar reasons, that's why the arrows go inwards on a negatively charged particle. It's because if I put a tiny positive charge near it, it will be attracted. If I put these two close together, their fields will merge with each other, and you get this delightful interplay where they kind of connect the arrows. Lovely. What is a coulomb? 1 coulomb is equivalent to 1 amp second. 1 amp times 1 second, which is a hint as to what the definition of current is, which we'll get onto in good order. The smallest possible charge is the magnitude of charge for 1 electron. This is the fundamental element of quantum mechanics. Quantum really just means a sort of discrete package. So energy is quantized. When we talk about atomic physics, we see that there's energy levels. But charge is also quantized. So you cannot have a charge that is not an integer multiple of the elementary charge. And the elementary charge is the charge of 1 electron, or indeed 1 proton, because the proton and the electron are equally but oppositely charged. What is the value of that elemental charge? This is a number that you should remember, depending on your exam board. I believe they used to, I can't remember about the latest version, they used to not actually give you that explicitly. They'd give you the mass of the electron and then the ratio of charge to mass. So you could work this out in the middle of an exam, but it's best to dedicate that number to your heart. Keep it close. We can use the elementary charge to determine the number of electrons flowing through a conductor. And indeed, this is how this fundamental charge was first discovered. An experiment using charged oil drops. Okay. Which I don't think we need to go into. We're not going to. But it's a nice experiment, but it's not fundamental. But you can deduce the number of electrons in any charged optical, whether it's a charged object, whether it's an oil droplet or otherwise. The number of electrons will be whatever the total charge is divided by this elementary charge. And you'll get the number of electrons, or the number of surplus electrons that your object is charged with. When I say surplus, I mean electrons that are unpaired with an equivalent proton, such that they don't balance out anymore. Right, when charge carriers, and by charge carriers, we're normally talking about electrons when we think of electricity flowing in wires. But within a battery, those of you who do A-level chemistry, you'll know that ions can also carry charges. You have the separation of an ionic fluid, and all the cations go one way and the anions go the other way. Enough chemistry. Just to point out that it's not just electrons who charge that. When we say charge carriers, we're not just talking about electrons necessarily. Electricity is the flow of these charge carriers. And a current is a measure of how many of these charge carriers are going past a fixed point per second. So if I have, yep, that's the drawing I wanted in the bottom left. If I've got my sort of casual observer at the side, and we are looking, I want to know, well, how much charge is going past a point per second is a useful thing to know, because it tells us essentially how fast the electrons are going. You can also then work out roughly how many electrons are going past per second, because although I was keen to emphasize that charge carriers can be ions, outside of a battery, it pretty much is just electrons. Okay, and so we have our definition of current. It is the rate at which charges flow. So how many coulombs per second are going past a certain point in a wire? A sort of speedometer for your electric flow. Conventional current is defined as the flow of positive charge. This is regrettable because electrons carry negative charge. And so when we draw a circuit, yep, that's the diagram I wanted. The convention is batteries, the longer side is the positive side, the shorter side is the negative side. Nice. And the current flows from positive to negative. Yep, that makes sense because we've said the conventional current is defined as the flow of positive charge, and positive charges would go, they would run away from, they would be repelled by the positive surface here, and they'd be attracted all the way around to the negative joint here. Okay, so the current flows this way, which is a nice convenient way to think about it if our charge carriers were positive, but they're not, they're negative. So the physical reality is that although the current is flowing this way, the electrons, I'll draw them in a different color. I was going to do yellow, but that won't show up very well. The electrons are actually traveling around the other way. And that makes sense because they are repelled by the negative. There's a word that's escaping my mind. It's really annoying me. They're repelled by the negative side and they're attracted round to the positive side. The trick of electricity then, the game to play, is that whilst the electrons are rushing around the circuit while the current is flowing the other way, we can use that to power devices, whether that's your smartphone or a light bulb or whatever, an electrical heater. In a circuit, current flows from the positive terminal to the negative terminal. To right. Okay, so bear those historical conventions in mind. But otherwise, when we talk about, when I talk about current flowing around a circuit, you could nearly always substitute in this sort of electrons flowing around the circuit. And if I do make a mistake as to, which way the current's flowing and which way the electrons are flowing, correct it in your mind. Put a little asterisk.